Hi students, I hope you're having a wonderful day. So today we're going to revise about introduction to differentiation and its related rate of change because your test is just around the corner. Now it's okay if you don't remember any of the formulas or you're having a hard time understanding, we can make it today and we can make it more fun and easy to understand. Right, so today we're going to learn about differentiation and some of its applications in real life. Okay, so now in the first things first, you have to know what is differentiation. So differentiation, or what we call a derivative, is defined as the rate of change. So in a term of function, the rate of change is defined as the um, rate of change of y to irrespective to x, or dy dx. No worries, we will get to this later. Now, the concept of derivative has been used in a small and large scale, such as temperatures or rate of change of shapes. For example, you see an ice cube melts at a volume of 0.5 meter cube per minute, but how much does it melt in each side every second? So this is some of its application in real life. So this is where we apply derivative. So like for example, to check the rate of change of volume of a cube with respect to its decreasing side, we can use the derivative form as dy over dx. Now we will get more into this later. So first, we always define our derivatives as the graph functions. So what you see in front of you here is a graph function of y equal to x squared. And what we got here is a curved graph. So now how do we apply a derivative formula for this graph? Now, when we are applying derivative for graph functions, we use it to find the gradient. So derivative at any point in this graph here, this point, this point, this point here, its derivative is called a gradient function. So if we calculate the gradient of yx squared, we find it the value to be 2 times x. So for every unit of x, the gradient is twice of its value of any point. So how do we interpret this? You see here in the graph here that when the value of x is increasing by each unit, for example, when x is equal to 3, we calculate the gradient 2 times 3 equal to 6. This means that every time the graph moves by a unit of 3 and the y-axis moves to a unit of 6, and the gradient keeps increasing. Inversely, if the value of x is on the negative side, or right here in negative 2, the gradient is negative 4, meaning that the gradient is negative. It's downwards here. So if we see that when it reached the point of 0, the gradient is 0. So what we can deduce from this graph function is that y is the function of x. So basically, y is equal to a function of x. And we write the gradient function as dy over dx. Please note that this is not a fraction. This is an expression, or basically a symbol of we define a derivative of y in respect to x. So by deducing the formula, we get y equal to x power of n. So this is n can be any numbers, integers, negative and positive integers. So when we derive these functions of y, or function of y respective to x, we said that the n, it will go to the front here and it will times with the function here, and the power will be minus by 1. So dy dx is basically the symbol for the gradient function of y equal to fx. So this is what we call a differentiation with respect to x. So for example, here we have y equal to x cubed. This is a cubic function graph. So when we derive it, it will become 3, we go to the front and times by x, and then 3 minus 1 is 2. So the derivative of y equal to x cubed is equal to 3x squared. So same with y equal to 2x squared. When we derive it or we differentiate it, we become a 4x. So on and so forth. And also that y can also be expressed in the function of fx. So when we say that fx is equal to fx cubic, the derivative of x, we call it f dash x equal to 15x squared. So there are multiple rules of derivatives, and we're not going to go through all of them, but we're going to go most commonly used in derivatives. So 4 of the rules of derivative is the constant rule, the chain rule, the product rule, and the quotient rule. So what are the differences between these rules? No worries, we'll get into that. So the first one is the constant rule. This is where we apply if the function is a constant, meaning that it's a number without any x in it, without a function of x. So for example, y equal to 10. So when a function is a constant, right? So we say that the amount or the number is equal to 0. Now, if we see this in the formula point of view, that y is actually a function of x. It's just that the x is equal to the power of 0 because x to the power of 0 is equal to 1. So when we multiply 0 by 10, we get 0. So that is why when we differentiate a constant, it becomes a 0. Now we go into the chain rule. So chain rule is where we apply the chain rule formula. So given that y is a function of v and v is a function of x, basically this is where we replace or we assume a function, a very long function is another function of v. So to find the dy dx, we have to find the dy over dv times by dv over dx. No worries, we've seen an example on this and you see how we apply this. For example, given here that y is equal to ax squared plus bx to the power of 1 of half. So how do we differentiate this function here? Because inside the bracket there's another function and there's a power outside. So by applying this chain rule, we can make this simpler in a way that to differentiate it. Okay, so we assume, given an assumption that the inside bracket here is a function of v, and then y is equal to v to the power of half, 1 over 2. So here we apply the rule, the differentiation of y towards v. So we differentiate y towards v over 1 over 2. We get this amount, we get this value dy over dv. And then the 1 over 2 we go to the front, and then the back is negative 1 over 2 because we minused it, right? And minus 1. Now, and then we times it by dv over dx. We have the function of v. V is equal to the expression of ax squared plus bx. So this is where we differentiate the value of dv over dx, and we get 2ax plus b. So by multiply all of this value together, we are able to find our first intended formula, our intended expression, which is dy over dx. Same goes to the second example here. We have a function in a bracket to the power of 4, and then we let v becomes the function on this bracket, so y equal to v power of 4, and then we move 4 to the front, and 4 minus 1 is 3, and then we just replace back the v inside the bracket with the original expression, and we times by dv over dx here. So dv, we know v is 4x cubic plus 3x minus 7, and it will become to 12x squared plus 3, and we are able to solve this. So this is, we differentiate the function if y over to f inside the bracket the gx, meaning there's a chain expressions there. Now, moving to the product rule. So when you hear about the word product, you know that it's a multiplication. So here's our example. If y equal to u times v, where u and v is the function of x, and then we can find the value of dy dx, which is using this formula, u dv over dx plus v du over dx. So this is the function when we applying product rule. So this is happen when there's two functions, they are multiplied with each other. We see an example here that y equal to bracket x plus 2 times bracket ax squared plus bx. So these are two different functions. So there's two ways to go about it. The first one is that we can expand the function here. We can open up this bracket here and solve it from there, or we can apply our product rule. So we assume that the first bracket as u and the second bracket as v. So by using this formula, u we put here in the front, which is x plus 2 times dv over dx. So we have a v here, and we differentiate dv towards dx, and we get 2ax plus b, and there's a plus sign. Remember, it's a plus sign, not a product sign, not a multiplication sign. And then equals to v, which is ax squared plus bx here, and times by du over dx. Since du over dx is x plus 2, so we cancel out the x, and 2 is a constant, it becomes 1. So we times this together and we get the expression dy over dx. Now moving forward, We have the quotient rule. So when you see quotient rule, you remember it is as in fraction. So this is where y over uv, and both u and v are a function of x. For example, fx over gx. So we imply this formula here, dy over dx equals to v times du over dx, and there's a minus sign, not a plus sign, u dv over dx over v squared. So now, how do we apply these rules? So here we have a function of y equals to x plus 2 over x plus 4. Whenever you see a fraction sign, you can apply a product rule. So you see here that we assume the top function here as u and the below function as v. So dy over dx is equal to, so v du dx, meaning that v here, the function of x plus 4 times du over dx. So we find du over dx here as 1 minus u, which is here, times x plus 2, which is above expression here, and dv over dx, which is 1 over v squared. So we have a v squared x plus 4 here, and we put a bracket and power to the power of 2. So this is the final result that we got. So this is a much easier example than you having to expand the bracket. So some of the applications of derivative in real life. So where do we actually use rate of change or differentiation? So one of it, the commonly used, is in business profits or loss. So some big companies, when they want to see the trends of their company, their profits and loss, we are applying the derivative. So we can see the tangent there or the gradient to see if it's going up or going down. Same goes to our temperature trend. So climatologists, they use differentiation to see the climate trend, global climate trends over the year, and also some seismology, which is the study of earthquakes, and also the study of speed, drag of a rocket missile. So this is the application in real life. So you don't have to worry. You need to only remember the formula and see how we can apply it in your life. Okay, so that's all for today, and I hope you're doing best for your exam. Right. Good luck.